This work is made in collaboration with Mikhail Ivanovic from the University of Belgrade. He is now in the Netherlands, and by a group of Ivan Božović, Jay Wu, and Anthony Bollinger. I will present shortly two findings of Božović's group about interface superconductivity, overdoped LSCO, undoped LCO bilayers, and measurement of penetration depth and finding of linear temperature, critical temperature dependence of phase stiffness, of superfluid density. And I'll give you some simplest explanations. This is simplest introduction to remind you about LSCO structure. Here is the phase diagram of LSCO. Here's the structure. Doping is given by replacing lanthanum by strontium or with extra oxygen. This is delta. And here we see the superconducting dome and nice empirical formula for TC as a function of doping level P. Okay. Next is the interface superconductivity in bilayer. Here you can see one metallic layer and one insulating layer. Metallic layer is highly overdoped LSCO with X is 0.45, and this is undoped insulating LCO. And you can see that both layers are not superconducting, they are insulators. But together they show appearance of superconductivity. Okay, the simple explanation is that we have migration of charge of holes from metallic to insulating layer, and in that way we adopt some copper oxide planes in the LCO, giving this superconductivity. Okay. Next is the very nice work of Božović's group. They made a series of bilayers with only one change, which is replacing by zinc some copper in the copper oxide plane, first, second, third, and -1, -2, and so in metallic. And you see that no damage on superconductivity, except if n equal 2, the second layer from the interface is doped by zinc, and the superconductivity is damaged. So this means that this bilayer superconductivity is completely two-dimensional, is one copper oxide plane superconductivity. In this specific case, it's n equal 2, and this is because of migration of diffusion of holes from metallic layer to the insulating LCO. Okay. Next, the interesting result was that in the first attempt they obtained maximum TC of 40 Kelvin, and they checked for very different level of doping for X in large from 0.16 to 0.42, and the result always was the same. The critical temperature was maximum. So nevertheless, overdoping in this LSCO layer, in the bilayer we have always maximum TC. Here is TC as a function of X, and also as a function of Hall constant, so it's the same result. What is the explanation? To describe the migration of holes between the layers, we have only two simple equations. One is Poisson equation, and the second is thermodynamic equilibrium. If we know how chemical potential depends on P, on density of charge of holes, we can solve easily these equations, and we can obtain a distribution of holes, profile of holes through the interface of bilayer. But we don't know what is chemical potential dependence on doping level. If we take Fermi liquid 2D, this is a linear dependence, okay? If we take one-dimensional, is square of P. But the result obtained with this assumption is wrong. So my guess was to take chemical potential dependence on P as a step function, 0 up to optimal doping, and after that linear dependence. After some time we realized that experimentally was obtained before. ARPES experiments by Ino and co-workers, they measured what is doesn't work, okay. They measured chemical potential as a function of doping level, and but they didn't believe in their results and tried to fit this by quadratic function. So having an idea that essentially cuprates are one-dimensional conductors, which is not the case. Okay, and also all the result of Božović and co-workers, they saw some mid-gap states, which means that chemical potential is constant. Okay, when we solve with this assumption of dependence of chemical potential on P, we obtain, as expected, something like this, and we can explain in this way that first, second, or third, depending on X, a layer is doped, optimally doped to the level of 0.16, and this gives the maximum critical temperature. It's easy to solve analytically, but to take into account the strontium diffusion, we solved numerically, including the strontium diffusion measured experimentally, and we obtained practically the same results. Okay, the next slide is experiment and theory. And in theory, we have we can identify in which level is in which not level in which plane, copper oxide plane, is realized this maximum temperature superconductivity, depending on X. Okay, and only for information, taking linear dependence of mu on P, the theoretical results is like this for temperature. It's not like this in experiment and the right theoretical explanation. The second, oh no, what is the explanation of this strange constant chemical potential up to optimal doping? Only shortly, one possibility is localization. So you see this from this point in underdoped regime for T below TC, we have some arc for T above TC, and above T star we have the full Fermi surface. This is one possibility. The second possibility is van der Waals curve of coexistence of two phase. The third is strong electron correlations. This is results of Kotliar. You see that for very large Coulomb Lipaldron we have insulator valence band and empty conducting band. Then in between we have mid-gap states, and finally for very low electron interactions, correlations, we have metallic state. Okay, one of okay. The second part is measurement of penetration depth in LSCO made by Božović and his group, and the result is that critical temperature is practically linear function of the superconducting stiffness or superfluid density at zero temperature, or that stiffness or superfluid density is this almost linear function of temperature. In clean case and in dirty case, this is when by replacing copper by zinc, the superconductivity is damaged. Finally, we have we have fit this experimental curve. This second curve is old for IPCO. You see, it's much better given by Hardy, and the upper curve is given by Božović and his group, and this is probably superconducting fluctuation, this square root dependence here. But you see that this simplest formula fit excellent. Even better, this is temperature dependence of the superfluid density, and of course we cannot take 2D ideal perfect Bose case because TC is 0, but we take some cutoff tau, which means that we have some along c-axis some three-dimensional motion, but very, very small. You see that tau, which fit these experimental results, is 5 to multiplied by 10 on minus 5, so Kelvin. It's very, very small. What to say? It's I have short time for this. Let me conclude. Two important challenges or for theory to take into account that chemical potential of holes is 0 up to optimal doping. So it's constant, independent of doping level, up to optimal. And also that that linear dependence of TC on phase stiffness is practically looks like local pair condensation in 2D Bose case. What is the explanations of these two points? Possible explanation is that we have two-component behavior. Two-component, not two-component liquids, bosonic and fermionic, but two different kind of collective motion of fermions, like bosons and two pairs, and like free fermions. Okay, thank you very much.
Thank you.
This is very convincing picture, and my question is just technological.
Okay.
Whether it's possible this to be confirmed by electrostatic doping? I mean,
Yes.
you have layer, then insulator, then metal, in order to use electric field to change the doping between electric field.
Yeah, absolutely. And people did that.
I remember
And
one time in
Ivan
Belgium.
Božović did
Yes.
he has few papers, I didn't mention this, but he has few papers that
You can give him the reference.
Okay.
Yeah.
that
We'll give you the
doping
reference, yes.
by clean doping. I'm
Yes.
calling clean doping because
Okay, I will contact with you
doping
later.
doping by strontium is
Chemical,
giving
yeah.
mess. Okay.
Yeah.
But this is very, very clean doping by the field. It's possible. Field effect. Absolutely.
We'll give you the reference. We have
The
that.
result is the same. Yeah.
Yeah.
Okay, thank you.
So I would like to ask you, in Kuparite, it was shown that the Fermi velocity is more or less compound and doping independent, down to very low doping, up high doping. How do you reconcile that with your story about the chemical potential?
I'm not sure that I have problem with hearing. It's not,
Okay.
it's not clear. Maybe somebody can.
He says you have the constant Fermi velocity
Okay.
in all these kind of Cooperates,
Yes.
right? And
Yes,
how do you
yes.
reconcile that with the conclusions here?
You know, we have not here real Fermi surface. This is the explanation. When we put holes in the system, in the copper oxide plate, that holes drops somewhere. Probably they localized and make preformed pairs. They're not.
And Masu,
Yeah, okay.
Masu Imada today showed very nice quasi-particle peak, for example, from ARPES in the underdog regime.
Okay, okay, but this is one result, one possible explanation. Maybe some other results.
Excuse me, I have a question if I may ask.
Yes, I don't hear you. Well, yes, please.
So there has been a relatively old paper from 1997 from Fujimori when they have been making these measurements, low-level photo emission measurements, and they have been showing for LSCO that this Fermi energy shift, chemical potential shift in the underdog samples was actually constant. Did not depend on the whole doping with respect to the undoped samples, and in the overdoped regime it changed. So this would be in correspondence to what you have been showing, but for the case of bulk compound. And then also Hashimoto have shown similar measurements for the bismuth copper-based compound. However, he did not see this Fermi level pinning, I would say. They still reported on changes in chemical potential, even in the underdog samples. So this LSCO compound, even in the bulk form, would correspond to your I think, to your data. But there is something special in the LSCO. It seems that other in the bulk compound does not show this Fermi energy whole doping independence.
Okay.
Maybe
Use the microphone. The microphone. Get the microphone.
Maybe it's specific for LSCO, but I'm not sure in that.
Okay.
I think that it could be general.
Thank you.